So where did all this come from? Well, what we're being told is this, that in the beginning there was nothing, and there was a fluctuation of that nothing which turned into something. The something blew up, basically, formed a bunch of energy, which formed into gas, which formed into matter, which then formed stars, which then formed into galaxies, and eventually there was planets along the way as well. And here we are to talk about it. Where does such an idea come from? Well, a lot of it comes from the work of a man named Edwin Hubble. Hubble was an interesting character in his own right for various reasons, but he was a pioneer in studying the redshift of distant objects. What is redshift? Well, if you see on this, what appears to be a rainbow kind of color here, this is sunlight that has been run through a spectroscope. And a spectroscope is something that breaks light up into various wavelengths. A crude spectroscope, for example, is a prism. If you've ever run sunlight through a prism, you notice that a bunch of colors come out the other side because the white light going in is then broken up into its various colors coming out. Now, if you have a good enough spectroscope, you can see that sunlight actually is not a continuous pattern of colors. You see that there's these vertical lines in here where there's colors missing. Turns out that when light passes through a gas, for certain reasons, the gas absorbs specific wavelengths of the light. So those colors are then subtracted from the rainbow spectrum that you would otherwise get. And by doing this, we can measure to see what gases are in the atmosphere of a star. For example, like I said, this is sunlight, so we can look at the pattern of lines that are produced and figure out what elements are in the atmosphere of that star. Interesting trivia point, the element helium was actually discovered on the sun before it was discovered here on Earth. They broke sunlight up and accounted for most of the lines, but there was a few left over in a new pattern. They said, well, this must represent some element that we're not familiar with. Thus its name, helium. It's named after Helios, the Greek sun god. So why are we getting into this? Well, because we have the sun as a reference point. I mean, the sun is a stable distance from the Earth. The Earth's orbit isn't perfectly circular, but we can compensate for that. When we look at faraway objects, though, and measure their light, it's a little bit different. Notice how there's a similar pattern of what are called absorption lines, but they're shifted as a group over in this direction, toward the red. As you might guess by the name, that's called redshift. What's going on here is that the light is effectively being stretched. Now, Hubble was among those who discussed the fact that we see redshift basically everywhere we look in the sky. There are a few objects that are blue shifted, meaning the light is being compressed in a sense, which means those objects are moving toward us, but everything else is red shifted. What does that mean? I apparently have a slide that's missing here because it illustrated that the stretching of light to form the redshift is an indication that that object is moving away from us. So since all objects at non-local distances are redshift, or at least their light is, Hubble thought, well, let's investigate this a bit further, and he correlated a lot of this data and realized that if everything is moving away from us, well, imagine taking a movie of the universe as all these objects move away from us. Run the movie backwards, and you see that everything gets closer and closer together until eventually everything would be at the same place. And this is the fundamental idea of the Big Bang model. If everything, with only a few exceptions locally, if everything else is moving away from us as time progresses, then looking backwards in time, everything would be getting closer toward us until everything eventually arrives at one spot. Therefore, that's how everything began. It all started from one spot and moved outwards. So again, this is the fundamental idea behind the Big Bang model. Now, of course, as a theory of cosmic origins, it has a lot of things to explain. It literally has to explain everything in the universe. And there's been a lot of work done on that. The Big Bang model itself, at least the current version of it, can produce primarily hydrogen gas in the beginning of it. According to the Big Bang model, the early universe was roughly 3/4 hydrogen, roughly 1/4 helium, a little bit of lithium, and maybe a scrap of beryllium, but nothing else. The Big Bang can't make anything else. Of course, there's a lot of other stuff, a lot of other elements that we have to explain. Well, scientists have worked on this and have constructed models for how all this other stuff was constructed in the centers of stars, and in some cases in supernova explosions and some other means. My point is that we are now told that we have a comprehensive model explaining where all of this came from. The Big Bang made primarily hydrogen and helium, like I mentioned. Everything else came along later in what is claimed to be a good model. Now, the third major element of the Big Bang is a prediction that was made. A while ago, it was realized that if the Big Bang were true, we would see something in the sky that's called the cosmic microwave background. Basically, looking out into space, we should see a slight temperature in all directions. Now, obviously, if you're looking at a star or a galaxy, you're looking at something hot. But even looking into cold space, space itself should be bathed in a very low level of radiation. This was predicted and then found. So in the early 1960s, the discovery of this was really the crowning glory of the Big Bang model. This is the one that really discredited the other cosmologies that were its rival at the time, and the Big Bang has pretty much been the predominant model among secular cosmologists since then. So those are the three fundamental pillars, really, of the Big Bang model. Redshifts, indicating that everything is moving away from us, therefore run the movie backwards and it all would have been in the same place. And then explaining where all the elements came from, and then a successful prediction of the microwave background. So this is primarily why the Big Bang is viewed as being good science today, because not only could it explain data that were already known, it also made a successful prediction.